Okay.
1.
You just like make the guess. It works or
Yeah.
something?
Then
Does
you
it
have
work?
the coordinates.
So you would think the coordinates are what?
Using that triangle, it would be 1/2 root 3 over 2 and then negative
1/2 comma root 3 over 2. So my question is the point 1/2 comma root 3 over 2, is that on the parabola y equals x squared? Like,
No.
is it true that 1/2 squared equals root 3 over 2? I don't think so. All right, but that's good. I'm sorry, I shouldn't have squashed that. I loved your volunteerism, and I should have just been like, oh, interesting. Okay, but it isn't quite right. And we can test that it's not right. Yeah, we can check our conjecture. Rafi wants in. You want to wade into this?
I was going to say you need to add a coefficient.
Okay. You could make it 1. I mean, we can't just say it's 1. We don't know whether it's 1 yet, but maybe 1 works though. I don't know. Is it 1 comma root 3 or something? Is that what you're thinking it is? But again, 1 squared is not root 3. Okay.
Theoretically, could it be like anything following the ratio of like 1/2 root 3
Yeah, exactly. So maybe we want to say it's like a, and then what is the other side? You know, like you could do it that way, and then maybe think if we have anything to narrow it down. The thing I keep checking you on, like I checked Rosie and Rafi both on this. I was like, is it true that your x coordinate, when squared, gives the y coordinate? Right, that was like my check for you, and it failed on both of yours, right? So, all right, so let's suppose that I did tell you the right answer. The right answer is a, comma, well, what should it be? I mean, it should be a, comma, a squared, right? We don't know what a is yet, but, okay? And over here, negative a, comma, a squared. And then keep in mind, too, that by a being the x coordinate and a squared being the y coordinate, if we zoom in on this triangle, what does the x coordinate measure geometrically? What does the x coordinate measure about a point? It measures how far away it is from where? From the y-axis is what the x-coordinate measures, how far away we are from the y-axis. So remember that by the coordinates of this point are a, comma, a squared, we mean that this distance is a, and this distance is a squared. Okay, I don't want to say anything more. You keep going, please. I mean, we kind of laid some foundations for this, but I don't want to be the one to solve. Go, keep going. You want me to check? I'll come around and check it and see if you get it. But that's like a helpful maybe start to this problem. I mean, the answer's right. I mean, once you get the right answer, you know you're right. You know, you check it, it works, then you know it's working.
I got the right answer.
All right, what else? Anyone else getting this here yet?
So you make an equation for both.
Prior to me writing this up here, if I had just if I were just to cover this a squared up, if I just showed you this triangle and said, hey, this side is a, and it's a 30, 60, 90 triangle, do you think you could tell me what this side is? You probably wouldn't say a squared. You might say something else. Don't say what it is, but maybe think about how you would have expressed this instead. Maybe there's another way to say a squared. I don't know. Keep going back to it until you get it.
Yeah.
Does it work?
Final answer is but that can't work. Oh, yes, it can. Yes. Right. Good job, Cameron.
Alright, I would love to have this conversation all day. In fact, this is like what mathematics is. Isn't it? Isn't this beautiful? I mean, this is fun. We're having some good discourse out there. Alright, listen. About, I don't know, a third of you have figured it out. So let's kind of come back together and hear how that was done. I do want to hear from you, Erica. Erica, actually, after I hear from someone else, because I think you did it in a very unique way. Maybe that's how other people got it too. But Eric has a. Oh, that's what Adele is. Cool. You guys should be friends. Okay. Perfect. All right. Tell me, what's going on out there? How'd you figure it out? Someone who I gave the blessing on a couple people. I was like, good job. Sabrina, I haven't heard from you today. Go ahead.
The way I did it was like, since you know that a squared should be equal to a cubed.
Okay, so this is kind of like what I was saying a minute ago. We also know, forget a squared for a second. You also know that's a times root 3 from like stuff we talked about yesterday. Do you understand her realization?
Yes.
You can say, you call this side a squared, you call it a root 3. Keep going. So
then I said them equal to each other, and then I got a.
oh, and then that's like game over. So a is, all right, and if a is root 3, then what are the coordinates here? Root 3 comma 3. I know how to square a square root, okay. And all right, I think the game is up. All right, so stop right there, and everyone agree with that?
Yes.
That does in fact work. And then just tell me, Eric, how you approached it, which is just creative. You got the same answer.
Yeah, with the right side.
Listen, this is great stuff.
With the 30, 60, 90 triangle, I basically made the hypotenuse of that triangle like sort of act as a line coming from the origin.
Okay.
And since the ratio of the two sides, given a squared and AR, the ratio is 1 and 1/3. Sorry, not 1/3, 3. Since, like, rather than 1, you can make the slope of that line root 3 over 1, which is just.
So what did you arbitrarily just? You said 1 and root 3.
Yeah.
Okay.
So the ratios. And,
You said think about this line,
yeah.
which has a slope of
Root 3.
root 3. Do you guys agree with that?
So you can make the equation y equals root 3x.
And then we have y equals x
Yeah.
squared,
So,
and you could find the intersections between them.
Since they're the y has to be the same at
I see it.
point, you make root 3x equals x squared. So
Do you like his solution? Isn't that great? Yeah, and then you find the intersection between this line that he came up with. No one else was thinking about this line, but he was, and I thought that was worth saying. But Adele was.
Okay, it's okay.
Eric and Adele were both credited for this amazing insight. Okay. And maybe there's another way to think about this problem. I mean, isn't that beautiful? I mean, isn't math wonderful? They both work. Math works. It's great. Rosie has something to say. She's excited about it.
I just have another way that I did it.
You have another way to do it? All right.
So I set up the proportion of.
Wait, Rosie. Listen, guys. It's Rosie time.
I set up the proportion of 1/2 over root 3 over 2 equals a over a squared.
Oh yeah. Okay. So I think this will yield the same equation, right?
Yeah.
So 1/2
Well, yeah,
over
so
root 3 over 2
equals a over a squared.
equals a over a squared. I think I already see all the way home on that.
Yeah, which turns into
Yep.
like 1 over root 3 equals 1 over a. And then
Great. Yeah. All right. There's so many good things. Alex, go quick. Make these comments quick.
Well, basically I just did tangent of 60, which is a squared over a. So tangent of 60 is root 3. So
Yeah, absolutely. Can you think about the tangent or another trig function if you like? Tangent's nice though because we've already written what the two opposite and adjacent sides are or whatever. Yeah, Maddie. Yeah. Noah.
A squared plus A equals the side squared. And
Yeah.
that's going to equal 2A.
A squared plus, it's worth noting that A squared plus A squared squared equals,
2A.
this is 2A. Did anyone stop to think about that? That this is 2A? This yields, if you solve it, the same answer, doesn't it? You get, in the end, the same A equals root 3 if you solve this. Which makes sense because where did we come up with the fact that this is A? And therefore this is A times root 3 in the first place? The answer is from the Pythagorean theorem, actually. So it makes sense that the Pythagorean theorem could come in and help us here too. So that's great. You guys are awesome. Okay. We would like to talk about the trig functions again today, but we'd like to extend them so that we can talk about the trig function of any angle. Not just acute angles. Yesterday was acute angles. Today we'd like to talk about the sine of 100 degrees or something, right? But before we can really do that, we need to say a little bit about what it means to have a big angle, right? I think the following things will not be news to you, but we consider an angle in standard position. This is like an arbitrary agreement among mathematicians. We consider an angle to be in standard position if we position it on the coordinate plane so that its initial side is along the positive x-axis. That's a new word maybe too, I don't know. And then the terminal side, we call the other side of the angle, the terminal side, is somewhere else. And we're opening counterclockwise. So that's maybe how we put alpha, this angle alpha, in standard position. And we think of an angle as now having like a positive or a negative association as well. If you give me a positive angle, I'm going to think about putting its initial side on the positive x-axis and then opening that angle counterclockwise. If it's negative, if you tell me, oh, I meant negative 30 degrees, well then I'm going to put the positive x-axis, go from the positive x-axis and go down 30 degrees from there, clockwise. So I think those are maybe terms you've thought about or heard before, and maybe also this term as well, coterminal angles. Those are two angles that have the same initial and terminal side, even though they may have different measures. Yeah. Have you not heard about those terms before?
Learn out this one.
Not yet. Okay. Yeah.
Where I was when I was not there. So since homework 4 is being assigned today, does that mean the speed trig quizzes could be tomorrow?
It could be any time. Yes.
It could be now.
It could be no. It can't be now, but it could be any moment. Yeah. It probably won't be tomorrow, but.
Yeah.
The first one is 5 minutes.
Oh, so it's like 4 minutes, yeah.
No, yeah, nothing, but it's 9 problems. All of them are 9 problems. The first one's 5 minutes, the next one's 4, 3, 2.
Do you have to do it as fast as you can, or can you take the full 5 minutes?
What?
You can take as much time as you like. I mean, inside the window, but I mean, it's fast. It's not a ton of time. It's not like you have like minutes and minutes per problem. You want to get them down to 30 seconds or so a piece is basically the idea, or less. Just the trig six. Yeah, they put a whole bunch of practice. I think 10 practice quizzes on Headline too, so you can check them out.
And then are you averaging the top 2?
No.
Or just all?
Dropping, they're taking 4 over the course of the rest of the semester, and we're dropping your lowest, that's all. So do well on them, please, yeah.
So it could be our first one.
Could be the first one, yeah. It could be. So let's find some coterminal angles to the following angles. Wait, I'll give you another 5 seconds. 1, 2, 3, 4, 5. All right, let's find some coterminal angles to 35 degrees. This is gamma. Is the Greek? We're going to learn some Greek along the way. That's gamma. It is Greek to you. Give me a coterminal angle to gamma.
Negative.
Negative 25 degrees.
What'd you say? Negative 325. Okay, give me another one that's coterminal to 35. 395. Okay. And for those who are like, wait, what? Wait. What are you doing, people? Adding or subtracting 360? Could you come up with another one? Yeah, more 360s. So like what? Like
395 plus 360.
I meant negative 6.
what is that? 745. Okay, cool. And you could come up with more, maybe too. What about B? What about this? Is what's the name of this Greek letter, by the way, on B? Beta. Give me some coterminal angles to angle beta.
30 degrees.
Not 30. Something else.
210.
210, I think will work. Anything else?
Negative.
Negative 510?
That's 10.
All right, and maybe other ones, neat, okay. All right, what's this Greek letter down here?
Omega.
Good job, it's phi or phi. Either way, it's
So he already knows what that's.
all right, so yeah, this is angle phi. How do we, stop because this is a more interesting one maybe. How do we find a coterminal angle of phi? Add, yeah, we don't need to change it to degrees. Maybe you're a fan of adding 360, but you don't have to add 360. You can just add 2 pi.
So 4.
So that would be adding 2 pi here, that'd be adding 6 pi over 3. So I like that. What would that be? Like 8 pi over 3 or negative 4 pi over 3? In general, could you list them all? Actually, maybe you could. You could say this. You could say 35 degrees plus 360 degrees times or any multiple of 360, right? So you might write it this way. So you might write it this way. In fact, right here, I've actually, all right, guys, I need your attention again, thanks. I've actually written them all now, haven't I? If n is 0, we get 35. If n is 1, we get 395. Stop talking, thanks. If n is negative 1, then we get negative 325, right? All of these angles are actually on the list I've just said. And by capital double struck bold Z there, I mean all the integers, right? Any positive or negative whole number or 0, right? And then same with down here, like if I wanted to do this one, I could write 2 pi over 3 plus, you can say, yeah, 2 pi n, right? Where n is some integer. So could you write them all? You actually could, yeah. If you wrote it that way, maybe. But the point, I mean, still the point that we're all trying to make is there are an infinite number of them. Yeah.
Do you want us to write them first?
I mean, I didn't. I just said find positive. I just said find some. So I didn't design you to do this activity this way necessarily. You did what I wanted. Good job. But someone could say name them all, I guess. In which case you'd have to say this. Or, I don't know. Give an expression that gives them all. All right. So now I think we've laid the groundwork. We've talked about big angles. So let's talk about what it means to take the trig function, sine or cosine of 100 degrees, or what would that mean? How would that work? Because yesterday, we want to kind of block yesterday out of our minds a little bit, because yesterday we didn't talk about those kinds of angles. So again, let's think about our angle. We'll call it theta, and we'll put it in terminal, and we'll put it in its standard position. And then here's my instructions to you, right? If you're going to have, I'm going to give you a theta, and what are you going to do? You're going to put it in standard position if it's not already, and then you're going to put a point somewhere on the terminal side of your free choice. And then I want you to compute, please, the distance that it is away from the origin, your point that you chose. Let's do that. You can use the distance formula or the Pythagorean theorem. They're the same thing, right? It's we're going to call it just, for short, we'll just call it r. But it's the square root of x squared plus y squared, isn't it? Is the distance there from the origin. And the reason I think r is a good name for it is because any other point that's that far away from the origin lies on a circle, and the radius of that circle is r, right? So r is a good name because like maybe it makes us think about circles. And actually this point is on a particular circle of radius r, along with all of its friends that are equal distance away from the origin. All right, and then, now once you've done that, right, I gave you an angle. You put it in standard position. You chose an arbitrary point on the terminal side. You computed the distance away it is from the origin, r. Now you're ready to say what the sine is, or the cosine is. The sine, our new definition, forget yesterday. Our new definition is the sine of an angle is y over r. The y coordinate that you chose for that point divided by r. And the cosine is x over r. And the tangent is y over r. And the other ones are up there too now. We'll define those trig functions that way. Interesting. And then I'd like to just kind of zoom in on this triangle a little bit here and take a look at it. Excuse me, there's no triangle yet. This picture. And then I would like to kind of like lay on top of this, literally, a framework from yesterday and be like, well, I'd really like yesterday to work still. Even though I can't put a 100-degree angle in a triangle, I'd still like to pretend. I don't know. So maybe we picture this triangle. Sometimes people call this the reference triangle. The angle I've marked here in white, let's just be clear, that's not theta, right? But it is an angle that's supplementary to theta, so maybe we care about it too. I don't know. And then if someone asked me, what's the sine of this angle, this white angle? The answer is opposite over hypotenuse. If you're a yesterday student, you're like, oh yeah, it's opposite over hypotenuse. I'm all about the sine. I know that. And notice that, thinking about our warm-up today, isn't the y-coordinate the same thing as opposite over, that's y over r. Actually, that's the same thing as opposite over hypotenuse. What does y do? The y-coordinate, that's just a measurement of how far we are above the x-axis. Perfect. So in fact, that's the same. Now the problem comes with now someone asking you the cosine of this angle, right? Because the cosine of this angle is the x-coordinate over the hypotenuse. Well, yesterday we might have said, well, it's adjacent over hypotenuse. Well, the fact that this is a triangle means that no matter when we do this, we get positive things, don't we? But here, in this particular picture, x will be negative, right? So that didn't happen yesterday. That's gonna like blow the mind of someone from yesterday. Wait a second. It's a triangle. So this analogy kind of breaks down, but in the first quadrant, it doesn't. In the first quadrant, it actually is all perfect. In the first quadrant, the definitions that we just put up, these six definitions, agree completely with our definitions from yesterday. So in that way, we've done something that I think we want to do as mathematicians. We've created more general, new definitions that are still backwards compatible to the old definitions, aren't they? It's like if you have a new version of Microsoft Word, you'd still like it to be able to open the old files with complete integrity, wouldn't you? That makes sense. We want this still to like work. And then someday, we might blow your mind even more. You'll take a class in complex variables. And someone will ask you, hey, what's the sine of 1 plus I? And you'll be like, I don't know. This wasn't good enough for that, is it? This definition is not good enough for complex numbers. But when someone finally hands you the sine function that's good enough for complex numbers, we'd like it to be backwards compatible all the way back to like geometry for our like friends in middle school, right? So that makes sense? We're trying to generalize. That's a goal we have as mathematicians, is to make definitions that are backwards compatible. Okay. So let's try this now. Let's put some meat on that problem we were just looking at. Say the point we were just talking about is actually -5, 3. So let's actually do it. Let's find the sine of this angle. We're going to call it angle omega, I guess. So omega is an angle with -5, 3 on its terminal side. Find all 6 trig function values. Let's go. Let's do it. Yeah. You're right. Maybe we should have said that. You're right. Maybe we should have said that. My apologies. Good catch, brother. Okay. Here, let's do this. So what do we need in order to find those? If we want to find like the sine, for example, we need to know it's going to be y over r. Uh-oh, we don't have r. What's r? Square root of something. (25 plus 9). It's not nice, but we can write it. It's the square root of 34, right? Is r. That's the distance we are away from the origin. Yeah, we'll just use that. So what's the sine? I think we're ready now to do it. What's the sine of omega? Y over r. So, yeah, 3 over root 34. What's the cosine? Yeah, it's x over r, using those definitions. What's the tangent? Y over r, isn't it? Oh, excuse me, y over x. So 3 over -5. And then the other ones, of course, we can write down too. They're the reciprocals. So root 34 over 3, just flip all those. 34 over -5. All right, neat. And then, all right, and then just for fun, can you guys also please do for me the same process now, just to practice with -10, 6. Go ahead. All right, and then when you're done with that one, do, if you will, do -500, comma 300. Could you do that then after you're done? I'm thinking this will keep you busy for a while. All right, keep doing it. Just for practice, you know, just do the process. Compute R. Go ahead, compute R. Wait, what? It's what? We get the same. We get the same answer. It's the same. Yeah.
I don't know if you could do this, but you could think of this as just the same rules as the other ones, but it's the angle of supplementary negative.
Yeah, you mean this angle over here? You're thinking about the reference triangle over here?
So
Is that what you're thinking of?
sine of it, like also opposite of hypotenuse.
Yeah, and then the only suspension of disbelief we have to have is when we get to like something like cosine, it's the side length here, which is -5. Sure, over root 34. Hey, it works. Let's go with it. Right, so yeah, that's exactly what I was trying to say on the previous slide. Yeah, it does kind of work, but it's kind of like, as long as you're okay with negative side lengths of triangles, then it's okay. And you also have to be okay with the triangle you're looking at actually doesn't contain the angle you wanted. Also, as long as you're okay with all that, then move forward. All right. So what's the answer to those? Why is that happening? Because we get the same answers? Yeah, these points are all collinear along the terminal array, if you want. Yeah, right? That's a great way to say it. In fact, could you prove that any point, any angle that has this on its terminal side, as if you have the point -5a, comma 3a, right? That you get, if you multiply both numbers by the same thing, do you always get the same result? Okay. All right, now, I said at the very beginning that when I'm finding trig functions of these angles, what I can do is put them in standard position, and then I choose a point on the terminal side arbitrarily. I can pick it wherever is convenient to me. So I say, why not pick it to be, just because I like the number 1, how about we pick it to be exactly 1 unit away on the terminal side? We get the same answer. We just discussed it, didn't we? We get the same answer no matter where we put it. So let's make it 1 unit away. And the set of all points 1 unit away from the origin, what does that describe? The locus of all points 1 unit away from the origin is a circle. And we call it, because 1 in mathematics we say unit. Unit means 1 in mathematics. It's called a unit circle. Okay. So maybe you've seen it before, but this makes all of our definitions really easy. If we choose to make it 1 unit away, then what's the sign of our angle? It's y over r, isn't it? But wait, now r is, so it's just y over 1, y. It's just y. And all of those trig functions become a little bit simpler if we all assume that r is 1. Because we can make r anything we want, right? So maybe we make it 1. So maybe you've thought about the unit circle. And that makes the coordinates of any point on the unit circle cosine, comma, sine. Right? That's a pretty elegant definition. So I think I'm about to give you is something that maybe you have already somewhere because you like cherished it when you were first given it. Maybe you made your own on a paper plate. I just did. Maybe you still have it. Maybe you modified this old like live forever. I am giving you a picture of the unit circle. And listen. Shh. Can you guys come back together with me? This is this picture right here. It's just a circle. It couldn't possibly be simpler. It's 1 unit from the origin. It's like the simplest circle I can think of. But now then we've made it a little more complicated by labeling lots and lots and lots of things. 16 points that are of interest to us. I have a picture of the thing you have on your sheet up here. And all these points that are around the edge, keep in mind what we've done. We've taken angles that we know and love. We've taken angles that we know and love, and we put them on here. And we have, we've highlighted the fact that out here, this is 1 unit away out here, right? These points at the edge of the circle are exactly, all of them are exactly 1 unit away from the origin. And that means the cosine, if you know the coordinates of that point, the cosine of this angle, 60 degrees, is 1/2, and the sine is √3/2. If you know the coordinates, then you know the cosine and the sine. It's a beautiful thing. Now, that being said, do you need to memorize all the coordinates on the circle? I mean, in some senses, yes. But it's super easy because here's the reason, right? Show me, this is the angle here. Can you guys stop talking? This angle right here, this line, this ray, if you like, maps to this ray under what transformation? This maps to this under what transformation? Yeah, it's a reflection over the y-axis. And you know, if you know the point here, then a reflection over the y-axis produces another point over here with the exact same coordinates, doesn't it? Except that x is negative. Perfect, right? And so symmetry gets you all the way through this whole thing. If you know these 3 coordinates right here that I've highlighted, you know the rest just by symmetry. And of course, you also know these 4 coordinates because you know what the coordinate plane looks like, right? And you know what 1 unit away looks like in each of those 4 directions. Peter?
Are you going to want us to rationalize 1/√2?
Doesn't matter. Yeah, you can say 1/√2. Yeah, absolutely. Yeah. Anything correct is great. Okay, so then now how do you use this? Now it's obvious to me if someone says sine of 7π/6. If I know where 7π/6 is, and I see it right here in my mind, then I'm like, perfect, it's right here. I know it's some big negative number, comma some little negative number. Well, the big number and the small number that I know is √3/2 and 1/2. So it's got to be negative √3/2 and negative 1/2. If someone asks me for the cosine or the sine of 7π/6. The trick might be, though, figuring out where 7π/6 is to begin with without this picture. So just to refresh your memory maybe about how do you maybe think about where those are. All the things over 6 are low and tight, 30 degrees away from the x-axis. X-wing style, right? X-wing style. You with me?
Yes.
Okay. All the things over 4, all the something pi over 4s are like X-man style. How about? Okay. Nice X. And then these, I haven't come up with like a good way to talk about these. All the ones that are 60 degrees from the x-axis up here and down here. Hourglass, something like that. Yeah, I don't know. All right, and then we need a way of thinking about where 7π/6 is. So how do we decide? In the first quadrant, we have 1π/6, or 1π/4, or 1π/3. In the second quadrant, what's the rule? 5π/6, or here? Someone says 3π/4. Why do you know right away that's in the second quadrant?
More than half.
I mean, certainly more than half of pi, and not quite pi, so that's cool. It's always going to be, the coefficient is always 1 less than the denominator, right? All right, we're going to practice this more and more and more. Don't worry. Come back tomorrow.